Hello, I'm Julio, and this talk is about dynamic Go instrumentation for production environments. If you're not familiar with instrumentation, it's mainly about being able to monitor some program behavior at runtime, and ideally without asking you to modify the program source code. So this is broadly used today by debuggers, profilers, fuzzers, and many software development tools, and you might also know dynamic instrumentation as monkey patching or simply runtime instrumentation. So this talk is about finding out a dynamic instrumentation technique for the Go language, but specifically suitable to production environments where we want a perfectly safe and fast solution. So we'll firstly have a look at the main instrumentation techniques we can leverage, select a solution among them, and finally design it step by step together. So quick words about me. I live in Paris in France, and I'm the lead developer of Sqreen's application security SaaS for the Go language. And by the time I submitted my talk to GopherCon Europe, Sqreen was acquired by Datadog. So I'll be now in charge of merging it into Datadog's Go tracer. Other than that, my software background and interests are mainly related to low-level system programming, language design and software architecture, and kayaking, snorkeling and barbecues are some of my favorite life hobbies when possible. So first, in order to perfectly understand what kinds of use cases we are targeting with dynamic instrumentation, we'll be using application security as our background use case and examples throughout this talk. So in modern application security, you will find RASP, which stands for Runtime Application Self-Protection. And this is the ability to add security protections to your running applications by monitoring their executions to detect and prevent real-time attacks. So let's take the example of an HTTP server serving HTTP requests with things like an external service request, a SQL query, and a file access. Once it gets deployed to production, the security team will want this HTTP server to be protected against potential security exploits. Like for example, the external service request could be vulnerable to server-side request forgeries, the SQL query to SQL injections, and the file access to local file injections. So the security team can leverage RASP technology and the underlying dynamic instrumentation it involves in order to protect this program. The other benefit of dynamic instrumentation is that the development team of this HTTP server doesn't need to do much in order to enable it. It simply needs to add an application security agent to this program in order to make it available to the security team. Once up and running on production, the security team can now manage the application security of this server while it is running live on production and without having to recompile nor redeploy anything. And so, for example, they could decide to enable the SQL injection protection, which will be added at runtime thanks to dynamic instrumentation everywhere SQL libraries are being used in the program. So if, for example, this server happens to have a SQL injection vulnerability, when an attacker sends its SQL injection attack, the dynamic instrumentation involved here should allow to detect and prevent the attack before executing the SQL query. And so, for example, we could decide to abort the function call and block the HTTP response. So this is our overall dynamic instrumentation goal, and let's see what can we do for the Go language itself now. The first thing to take into account is that Go is a compiled language. We write Go source files that the Go compiler compiles into a binary program file. Then at runtime, this binary program file is loaded and executed as a process on a given operating system and hardware. From there, we can take a look at the instrumentation techniques we could leverage. Instrumentation happening at runtime is called dynamic instrumentation. Trap-based instrumentation is by far the most famous one as we use it on a daily basis with debuggers. And so it relies on software traps added to the running program's code so that its execution gets trapped and paused. So it commonly relies on operating system support, higher execution permissions, and the main downside of this technique is that the program's execution is slowed down due to the context switches it involves. Then the next famous dynamic instrumentation technique tries to avoid those performance issues by directly rewriting the program's code at runtime. So this has definitely the benefit of no longer relying on the kernel when executing the instrumented code, but it still requires higher execution permissions, and its support is considered complex due to the reverse engineering techniques involved to modify and inject the binary code. So the use of this technique in production is too unsafe and dangerous for now, as any mistake would lead to program crashes. Then instrumentation not happening at runtime is called static instrumentation. At the source code level, we have source code instrumentation, either manually added by developers or automatically performed by tools such as GoGenerate for Go. At the compiler levels come compiler instrumentations, and the Go compiler, for example, provides some of them, such as the code coverage mode, which automatically adds extra code into the compiled software during its compilation. And finally comes static binary rewriting of the binary program file. And this technique is similar to its dynamic alternative, but with the benefit of being applied to the program file on the development environment. So it's by far less dangerous than its dynamic alternative, but still has the same portability and complexity issues. So overall, each of these techniques have their own pros and cons, and none of them, unfortunately, exactly provides what we are looking for. So in order to target production environments, the trick will be to leverage static instrumentation to avoid runtime problems, limitations, and risks. So at runtime, to make the dynamic Go instrumentation solution fast and safe for production environments, we need to avoid every single runtime issue that we previously listed and rely on statically added support for it. This problem actually already has a commonly used solution, which is adding software hooks at compilation time to the program and use them as building blocks of the dynamic instrumentation. So our Go source files need to be compiled with an extra compiler instrumentation step, adding hooks to the compiled Go functions, and the resulting binary program file will be instrumented and have the hooks listed into a table in order to be able to find them back at runtime. Then at runtime, a companion package can be built and rely on those hooks in order to provide a high-level and idiomatic dynamic instrumentation API. So back to our HTTP server example, once compiled with this static instrumentation, our points of interest are now instrumented with hooks. They can be found using the hook table, which is indexed by function symbol name, and we can build the dynamic instrumentation package providing a convenient high-level API allowing to attach a Go function callback to an instrumented function. Then we can build the application security agent on top of it, receiving even higher level instrumentation instructions, for example, coming from a backend. And it has now everything required in order to dynamically instrument this program. So congratulations, we just figured out a dynamic instrumentation solution that is suitable to production environments. Nothing unsafe is being required here, and everything happens in user space within the same process. So now that we know what to do, let's see how to do it. So we'll start with the compiler instrumentation because this is the building block of our dynamic instrumentation technique. The big challenge in order to be able to add our compile time instrumentation is to figure out how to integrate into the compiler and where in the compiler do we perform the instrumentation. So we need to take into account the compiler being used and the user experience we want to provide. In our case, we know that we're targeting the standard Go compiler and that we want the best possible developer experience because they are the one who will integrate the solution. So we want it to be as simple, efficient, and standard as possible, and ideally without requiring to change anything in the standard compiler. So the idea is to provide this compile time instrumentation as a standalone tool externally integrated into the compiler. Regarding the Go compiler now, it currently doesn't allow to externally add an extra compilation stage without modifying the compiler itself. But fortunately, the Go compiler has a command line option allowing to call an external tool when invoking each Go compiler toolchain program. This option is tool exec, and its value must be a command line that will be called to execute the Go compiler toolchain programs involved during the compilation. So the overall design of this tool when compiling a Go program from a given main package is that the compiler first creates its package dependency tree. Then it calls the compile toolchain program for each package of the tree. And so this is exactly the moment where we can intercept the calls to the compile toolchain program in order to perform our source code instrumentation. And so now for each source file of the packages that need to be compiled, we can instrument them one by one and save them into the build directory that the compiler has created along with the list of hooks. Once we are done, we can then forward the original call to the actual compiled program, but now using the instrumented package source files in the build directory. So the result is therefore the instrumented archive. Now when compiling the main package, a few more things must be done. It goes through the exact same source code instrumentation as previously explained, but because it is the last one being compiled, we need to finish by generating the hook table as a data structure. So the tool reads the list of hooks and generates the hook table as a Go data structure into a new file in the build directory. So then it similarly forwards the code to the actual compiled program, but also adds the extra Go file containing the hook table to the list of files to compile. So the main package gets compiled into its archive, and the Go compiler can finally move to the last step, which is linking the program. So it calls the link toolchain program with a list of instrumented archives, and we don't need to do anything else but forward the execution to the actual link program, which will produce the instrumented binary program file. So in the end, this instrumentation tool is basically a proxy, having two major technical details to note. The first one is that it is called after the dependency tree was created, meaning that it is not possible to add new package dependencies into the instrumented source code. And second, the tool is executed several times throughout the overall compilation, so sharing data between them is achieved with temporary files in the build directory. And finally comes the funniest part of this talk, which is the actual source code instrumentation that is performed by the instrumentation tool. So the principle is simple. The source code instrumentation living in the instrumentation tool parses Go files and generates the same files but with hooks added to their functions. So it's just a matter of using the Go parser of the standard library in order to parse the package source files, work the function definitions, and add hooks to them. Again, the goal is to be able to monitor function executions. And for example, this is the interface of the SQL execution method in the standard library. The hooking model we will define here will allow us to monitor the entry to the function thanks to the prolog hook and the exit from the function thanks to the epilog hook. So let's implement it together step by step now. And just please note that the following code snippets are not thread safe for the sake of readability. So first, the epilog. In order to monitor the entry to the function, we will simply define the prolog as a function value expecting the same arguments as the instrumented function. And note how such function value can be nil, which will be the value to use in order to disable the hook. So at runtime, when the prolog value is not nil, we can call it and pass it the function call parameters. So here is the call to the prolog. Now for the epilog, we can similarly define it as a Go function value, which this time expects the function results of the instrumented function as arguments here. So at runtime, we also call it when it is enabled after the prolog hook. And note the nice trick here with the function closure around the epilog call, which allows to bind the function results to the function closure. And so this combined with the defer statement allows to call the epilog function from any following return statement along with their return values. And so this is a really nice property of defer that simplifies a lot the source code instrumentation because we actually don't have to instrument every return statement of the function in order to monitor its return points. Now for more advanced use cases where the epilog depends on the prolog, it is actually simpler to have the epilog function as a return value of the prolog so that they can share local context together through the function closure. So the prolog type changes a little bit so that it now returns the epilog value. And at runtime, we simply need to check the prolog return value and call it when it is not nil. Now to go beyond pure execution monitoring and be able to abort the function calls, we will add a second prolog return value that tells us when should we immediately return from the function. So we slightly change the prolog function type so that now it returns the abort boolean value, which when is true means that we immediately need to return from the function. And so the last missing piece is being able to change the return values. So we are changing the epilog function type so that now it expects the instrumented function results by address. And so we pass them here by address so that the epilog can change the return values when required. So the hook API we define now allows us to add runtime instrumentation that can detect an attack in the prolog hook and abort it by returning specific values from the epilog hook. So when entering the exec method, having the SQL protection attached to its prolog hook, we will now be able to check if the query string has an injection, and when it does, we will be able to return the fact that we do want to block along with an epilog hook that will be able to override the return error with a non-nil error. And so here is the underlying code behind it. And so following the hook API we defined, you now know that the prolog type depends on the instrumented function type. And so when it doesn't has an injection, we simply return the fact that we don't want to block along with no epilog. And when it does have an injection, we return the fact that we do want to block along with an epilog that will override the return value. And last but not least, the hook table code generation. That is a pretty straightforward data structure that is here to provide us everything we want to have access to at runtime. So its entry point is an overall instrumentation descriptor that points to an array of hook descriptors, which point to the Go interface values we want to be able to retrieve at runtime. Then to find it at runtime, we simply export its symbol name so that the dynamic instrumentation package can link against it. And our last step is the dynamic Go instrumentation package where all the magic happens. So the dynamic Go instrumentation API is pretty simple. It simply provides a find function which expects a given function symbol name. And so here is the symbol name of the exact method of the DB type in the SQL package. So then it returns you a hook interface value whose attach method allows you to atomically attach a given prolog to it. And so now you know again, here is back the prolog definition here, which again depends on the instrumented function type. Another alternative the package provides is to have a reflection-based prolog definition. This prolog would get the instrumented function parameters and results as reflection values. And so then you can dynamically attach it to completely distinct functions and up to this function to do the job and runtime in order to adapt to them. There are three internals I wanted to show you. The first one is reading the function symbol name. So given the hook descriptor having the prolog variable and function interface values, we can use the reflection package and get the function interface value address, pass it to the func4pc function of the runtime package in order to get the function descriptor whose name method gives you the function symbol name. Now, in order to check the callback type and check if it is compatible with a given prolog variable, it's a matter of comparing the type of the prolog variable with the type of the callback interface value. When different, it means that the types are not compatible. Then the magic behind the dynamic prolog lies behind the use of the makeFunc function in the reflection package, whose first argument is the type of the function we want to create. So here we want to create a function that is suitable for a prolog variable. And so then this reflection function does what it takes at runtime in order to bridge the actual function type with this reflection-based function. And so it is demo time. So we have here an Hello World Go module whose hello.go file we simply call the printline function with the hello string. And for the sake of the example, I've created an instrumentation.go file that will instrument the printline function from the init function so that it is called before the call to the main function. So basically here we find the printline function using its symbol name again. And we're now able to dynamically attach to it a prolog and an epilogue that will log the function call parameters and the function results value. So now we're installing the instrumentation tool, and we'll now be able to compile the module with a few options. The first one here is the -work option, which allows to keep the working directory, so the build directory of the Go compiler. The -a option, which allows to recompile everything, including the standard library, because again, we want to be instrumenting everything. The -x option, which allows to have the full logs of the Go compiler. And then we pass the instrumentation tool through the tool exec option with a few options we have in this tool, the verbose mode and the full instrumentation mode, because by default, we don't instrument everything. So here are the logs of the Go compiler along with the instrumentation tool logs. And so when we are done and we scroll back a bit, we find back here, for example, the format package, along with the Sqreen instrumentation tools that will give us some details. So the fact that it is instrumenting the package, along with the list of files that it is parsing in order to instrument them. So the result is 123 hooks added to the hook list in the end. And we finish by forwarding the call to the actual compile to chain program. But this time we are changing the source files by the one that have been instrumented in the build directory. Now, if you scroll down a little bit, down to the main package, it does again the same, but this time it is also creating the hook table as a Go data structure. So we see here that it has more than 1,000 hooks read from the list of hooks into a Sqreen hooktable.go file. And so then it forwards the call to the actual compile to chain program, along with the instrumented hello.go file and the hook table. So now if we execute it, we will get the expected output, which is the call to the printline function, along with the instrumentation we've added, so the prologue and the epilogue that were logging the function parameters and return values. So in the prologue, we see the array having our hello string, and in the epilogue, we see the two return values of the function, which was the number of bytes that were written and the error. So 6 bytes were written and no error were returned. Now, if you have a look at the Go build directory, here is the tail of the list of hooks. It has all the symbols that were created during the instrumentation. And then if we have a look in the main build directory, we can have a look at the hello.go file that was instrumented. And so we will find back our main function along with the instrumentation block that was added to the function. And last, we can have a look at the hook table that we generated. And going at the bottom of it, we will find the instrumentation descriptor, which points to the hook table array. And so the hook table array, again, has all the descriptors to the instrumented functions so that we can find them back at runtime. So I hope you enjoyed the ride, and I really think this is an excellent example of how composable the Go ecosystem is, and the fact everything here is written in pure Go is also a great proof of language maturity. Now, if you want to give it a try or go into further implementation details, you will find everything in Sqreen's Go agent repository. And of course, stay tuned to see what's coming next in Datadog's Go tracers.